Hello, everybody. Good morning, good afternoon, good evening, depending on whatever time zone you happen to be in. I'm so glad that you can join us. Today's episode is sponsored by SimScale, and it is about running fast, accurate, scalable multi-physics simulation in the cloud. Now, before we start our webinar today, I wanted to give you a few tips and reminders so that you can get the best possible webinar experience here. If you have questions about today's topic, or if you have questions for the panelists, you can submit them into the Q&A box at any time. We'll address your questions, as many of them as possible, in the live Q&A session after the demonstration. I have to remind you that today we are not doing just another CAN demonstration. This is going to be a live software demonstration that tells you what is possible instantaneously, so get ready for that. You can also download a PDF copy of today's slides. Well, the slides that are available, not the live portion, obviously. The PDF slides, and check out the resources related to the topic from the resource list to the left side of your window. If you are experiencing any technical problems, please visit our webcast help guide by clicking on the help ? Icon at the bottom of the console. Now, if the slides are not advancing, you might want to try refreshing your browser. That usually solves the problem and give you back good visuals. So let's talk about today's topic. Engineers often talk about the difficulty of running simulations on a workstation. So fast, maybe. Accurate, maybe, but can it be fast, accurate, scalable, and also multi-physics? Probably not on a workstation, but in a cloud, it is possible. So we'll show you how to do that. And let me just go ahead and invite my panelists to join me. David, welcome. Hello, how are you doing?
Thanks a lot, Kenneth. Doing very well. Pleasure to be here.
Very good. David, first, would you mind saying hello to the audience and just tell us about your background and give us a few information about who you are?
Of course. To everyone in the audience, welcome to today's session. I'm David, co-founder and CEO of SimScale. My background is in applied mathematics and mechanical engineering. We have co-founded SimScale 9 years ago, and ever since we have been at it of making simulation technically and economically more accessible. Back in these days, I'm not running as many simulations as I used to, but hopefully it's still going to be sufficient for today's session. So I'm really looking forward to the next 45 minutes.
Very good, David. So I'm going to let you do your screen share and then show us how to do simulation in the clouds, and I'll watch it alongside the audience. Off you go.
Sounds like a plan, Kenneth. Let me bring up my screen. Kenneth, could you confirm that you're seeing a slide share now?
Absolutely. You're live now, David.
Excellent. Good. So, Kenneth, thanks a lot for the introduction. You said it already very well, so I want to keep this very brief. Just for everyone, what to expect over the next 45 minutes is that, and with the danger of stealing a bit the thunder of it, I'm going to show 3 different simulations on this model. We're seeing here a high power electronics equipment, in this case an EV inverter, which is a great model or a great product because it involves many different physics that we're going to all simulate today. And I'm going to do 2 of them completely live, 1 of them partially live, not with the intention of, like making this a training or making this a sophisticated, onboarding session for a simulation tool. No, more to show that that this can be done end-to-end with little time investment, and to encourage you to try this out yourself. The beauty of a tool that's being completely cloud native is that it's just a browser window away. So everything you see today is not something you don't need to install anything, you don't need to download anything. You just need to create an account on simscale.com. And then you can try out these simulations for free. I'm gonna later on give links to tutorials that give you step-by-step instructions. So if there's a part of today's session that is a bit too fast or that you haven't understood, you can repeat those sessions on your own speed later on. With that, I'm going to start just 10 to 15 minutes, bit of a theoretical part about, quick introduction of SimScale, I guess our view of the world, why we've built SimScale the way we did, and then we're going to hop over into the practical hands-on session. And with that, without further ado, let's get to it. As a company, we've been around since just south of 10 years, have about 100 team members. And over the past 10 years, we've onboarded hundreds of thousands of users to SimScale that ran millions of simulation jobs. And throughout all of, we were fortunate enough to work with thousands of engineering organizations that that we could learn from, and where we saw issues, bottlenecks, troubles they had with deploying simulation effectively. And really, our mantra at SimScale is all the time, or has always been, empowering engineers to innovate faster. And the aspect that I like to stress here, and that I want to stress before we go into the demo, is that we do that by making simulation technology technically and economically more accessible. And I like to say that because there's a lot of methods and meshing algorithms and solvers, etc., on SimScale that we take a lot of pride in, for sure, that are also very powerful. But the unique aspect of SimScale is the accessibility, and I'm going to get into that later on. And when we talk about accessibility, we not just mean accessible in a browser. I think there's a deeper meaning to that. And over the next this will take me sort of 3 to 4 minutes to explain a bit why we've built SimScale the way we've done it. And with that, at the top, you can see a sketch of the overall product lifecycle, from conceptual on the left, product ideas, through all the way to manufacturing and then putting a product into operations, and how the traditional way of using simulation looked like. It somehow looked like this, right? A bit simplistically, but it somehow looked like that. You typically have an on-premise hardware stack on which certain middleware runs, and then some software, depending on typically for each physics a specific type of software, and then a different vendor supporting that software. And the challenges of that, and that's great. This has a lot of organizations have adopted simulation this way. A lot of value has been created by simulation this way. But because it's such a hard to maintain, hard to roll out stack, it's typically only used in the latest stages of the design process. So when a design is mature enough to actually be handed over to the simulation group, to the methods group, to the analysis group, to run some final simulations on it before a product or design moves on into manufacturing. And the pity of that is that a lot of the value simulation could create in other stages of the product lifecycle is not being leveraged. And that starts with informing the design process in the hands of the design engineer, the project manager that drives the design, not for final validation, but for informing design decisions earlier in the process. But beyond that, there's more. Right? There's more novel topics such as generative engineering, design space exploration, shape optimization, or all the way to the right. A hot topic these days is simulation in support of operations use cases as part of a digital twin setup, where we would look at things such as predictive maintenance, improving operational efficiency, these types of things. So in all of these use cases, simulation could create a lot of value, but it's hard to do that with a stack, with the traditional stack that is around today. And so a driving thought behind SimScale was always sort of, how should a simulation hardware and software stack look like to support all of these use cases and to make simulation technically and economically more accessible? And it starts with our conviction that the IT layer is a non-differentiating factor for engineering organizations, meaning that in the long run, we believe not all IT, but a big portion of the enterprise IT will be outsourced, because any engineering organization needs to have it, right? So it's non-differentiating, so it's going to go outside of the organization. And so in this case, we take care of all the required compute infrastructure to run those simulations at any scale. On top of that infrastructure, we integrate a bunch of best-in-class simulation technologies, some of them open source, some of them commercial via partners, some of them developed in-house. And we integrate those technologies together to end-to-end physics workflows. And that starts with, and we're going to see those later in action, that starts with a whole host of different structural analysis capabilities, different thermal capabilities, from conduction only over convection only, and then fully coupled convection, conduction, radiation, and then going into the fluid realm where we have different types of analysis that cover all sorts of fluid and airflows. Now, all of these physics are then made available, and that's, I think, what most people know SimScale for, is a SaaS application, so a web application where all of these physics can be simulated end-to-end from a CAD model to the design decision inside a browser. And that's what we're going to see today in action, in the next half an hour. Now, what not everyone knows about SimScale is that all of this is also accessible programmatically via an API. And so the entire simulation capabilities that we're seeing down here can be not just driven by a graphical interaction, but also programmatic interaction. And that is especially useful in those other use cases that I touched on earlier. Again, that we don't have enough time to go into detail today. But if you're interested in shape optimization or design space exploration, there's a lot of content and different demos and customer examples available where SimScale has been used in shape optimization workflows. Or we're also involved in projects for digital twin setups where oftentimes the simulations are ran automatically, driven automatically by some other piece of software, and not graphically anymore. Let's be honest, this is a fairly busy slide, so let's make sure we move on here, because what we're going to focus on today is just this part. We're going to focus on how can engineers run multiphysics simulations in a scalable way, fast and accurately, using a SaaS application. That's what we're going to see live in a second. Before we do that, before we go into the actual hands-on part, a last slide, just to make sure, again, that this isn't seen as yet another demo I'm looking at, because I'm going to show some physics later on, and I'm sure a big portion of the audience has seen similar physics simulations before. So what's unique? And I want to spend 2 more minutes on that one before we move on. On the right, we can see a little, similar as to the slide before, a little sketch of the product lifecycle from concept to production. And on the y-axis, we can see the product performance and cost. And what everyone, I think, is aware of, if you think about, it doesn't matter which product, if you think about how the performance of a product is realized and how the cost of a product is realized, it kind of looks like this. Like this curve here. The concept phase and even the detailed engineering phase is typically, not very costly, because this is where engineers, exchange ideas, document ideas, drive design. Where it gets really expensive is the moment the supply chain is being set up and sourced. And then, of course, going into production, this is where most of the cost occurs. Now, what's interesting is that if you think about how the cost and the performance of a product is being defined, it's almost an inverse or a mirrored version of this curve, where we can see that the biggest, the most impactful decisions that define the performance of a product or the cost of a product are in the earliest stages. And I think this is, as engineers, this is intuitive to us. But at the same time, if you think about how simulation is being used today, it's not in line with this intuition or with this chart, because mostly, and again, I'm using a simplistic way of representing this again, but most engineering organizations have designers, engineers, project managers drive the earliest stages of a product design process to then bring in the simulation expert fairly late when there's mature designs available. Answering specific what-if questions, answering specific physics questions to validate the design and to move on. Now, SimScale has been perceived in a way that we go away from siloed, tools that only a handful of experts have access to a more central layer. This is how we envision, or this is how SimScale is used in most customer organizations we work with today, as a platform where both the design engineers and the simulation experts have access to and can collaborate on. And as such, you can capture and share simulation expert knowledge. Designers and engineers can reuse, and by that, have simulation be used much broader, earlier in the design process, broader in the organization, making better design decisions earlier. Now, this is, I think, a concept of that a lot of, vendors and a lot of, associations have promoted for a long time, because, again, I think it's intuitive that the early use of simulation makes sense and the broad use of simulation makes sense. Now, the practical part to this is very hard. To make this practically work, it's harder than it seems because, for decades, this has been tried with, medium success here and there, but it's not like that most engineering organizations today are simulation driven. And our perspective on what it takes to make this actually work is a set of 4 criteria for a tool. The first thing is, we're going to see that later, is that a simulation solution to enable such a use of simulation must work anywhere, anytime. With anywhere, we mean not a VPN that certain people have access to, where you need to take care of uploads, downloads, and whatnot. Anytime means no queues in HPC clusters, no waiting until the cluster is free to get an answer done. Good design today happens completely collaborative, completely distributed, asynchronously. So the tool needs to support that. The second one is, if a design engineer has the need for simulation once in a while, once a month, every 2 weeks, he or she will not adopt a tool that is hard to learn, hard to use, right? It's not going to happen because there's simply too much, activation energy until to build those habits. So the tool must be easy to learn and use. The third one, a principle that we believe is important, is collaboration, knowledge sharing is very important. What I like to say is that simulation is worthless if the person driving the simulation doesn't trust the results. And trust in the results doesn't come from, just a tool or, a brand. It comes from actually other simulation experts, people that have done this before, acknowledging that this is a good simulation setup, sort of coaching, teaching, sharing the knowledge. And for that, collaboration is key. So bringing simulation experts and, simulation novices on the same platform is something that's important. And then the last one, capable and robust. And that's almost like table stakes from our perspective. If a simulation tool doesn't solve the physics challenge at hand, there's no point in starting to use it in the first place. Now, the reason why I wanted to convey that is we're going to go back to this slide now. In the next 30 minutes, we're going to have some fun with SimScale, and we're going to set up a few simulations. But I want to get back to this slide and going back to these points to make clear what's the unique aspect about SimScale? Why yet another simulation tool, you might ask? And so I want to make sure that these points come across. Good. You made it through the theoretical part. I promise from here on out we're going to have some practical fun with SimScale. So what we're going to do is we're going to take a look at 3 different simulations together. 2 of which are going to run end to end. One, takes about 2 hours. So unless you want to stick around with me for 2 more hours, we're not going to do that end to end. And we're going to use a model that we can see here on the right. This is a piece of power electronics, water cooled. I have that's an inverter. So we have different capacitors in the middle. We have other, semiconductors mounted. Typical for these power electronics assemblies or equipment pieces is that there's a lot of power that needs to be managed. Hence, we need it to be liquid cooled. And so it's an interesting application because depending on where, oftentimes these things go on a vehicle. So you're concerned with vibrations, and because it's liquid cooled, you're concerned with the sizing of the pump. So you want to make sure that the pressure drop across the flow channel is minimized. And lastly, of course, you want to make sure that the electronics components mounted on this part are operate in safe temperatures. And so very different physics that we're going to take a look at all of them now in the next 30 minutes. For that, I'm going to quickly leave my, you shouldn't have seen that. I'm going to quickly leave the presentation, hop over to my, open up a new tab. And I think what I like to show keep in mind, anywhere, anytime. Right? What you're seeing now is my is a browser window. And so what I'm going to type in here is simulation.new. And that's a URL that we bought once at SimScale, and I think it's a nice gimmick to convey the idea of simulation anywhere, anytime. So I'm at some browser. I type into my URL into my browser window simulation.new, and what it does, it opens up SimScale. If I'm logged in, I get directly to the project creation dialog, and I can create a new project. I'm giving this a name. It and it directly opens up the SimScale web interface. It asks me to import a geometry. I bring in a model designed in SolidWorks locally, and I'm bringing this in as a parasolid into this one. Now, quick pause here, right? Anywhere, anytime. I think the important aspect here is, of course, the simulation.new is a bit of a gimmick. I think it's a nice thing to do. But the important piece here is I'm sitting at a $600 laptop. I'm running all of this web conferencing software while I do that, and I just created a new simulation project from the convenience of my of a browser. And I think that's important in today's world of where design happens decentralized, happens fast. When we want to make design decisions earlier, we need to equip our designers and engineers with access to these tools. And that's what we mean with, that's where the browser and just running end-to-end in a browser comes in very handy. Now,
right. While you're waiting for it, David, I thought maybe we can chit-chat a little bit about what's exactly happening, because people have some misunderstanding about SaaS software. Are we talking about issuing commands to a software that is running in the cloud, or does the software get cached? Or could you clarify a little bit about that?
Happy to. So this is we like to call it a cloud native application, because to underline the difference, this is not running this is not a remote desktop where some operating system is running and I'm streaming something through here and I'm streaming pixels. This is a cloud native application that has been built for the browser. That means nothing is persisted locally. So nothing is persisted on my side. It's just a web application such as Gmail or Salesforce, or it's a native web application, and that means, and it's highly optimized for for graphics interaction. You can see this one. This is now rendered on my local GPU, so we're making heavy use of WebGL, but all the heavy lifting operations are such as mesh generation, CAD operations. We're going to see them in a second, as well as the simulations are done server side, and so I have nothing to worry about with respect to data transfer, etc.
Very good. Thank you so much. I see that it's pretty responsive, so I'll let you go ahead and run the simulation now.
Good. Yeah, let's do that. Quickly before we do, just to make sure, because I actually wanted to quickly jump back to the slide, just that everyone understands what we're going to do. We're going to run these three analyses. So the first analysis we're interested in is the easiest one. We want to get a feeling, or we want to quantify the pressure drop across this water jacket. We want to make sure that the volume flow I'm pushing through, what is the pressure drop, hence to design the pump or to size the pump. Second, assuming this piece of equipment would be mounted on a vehicle, we might be interested in a vibration analysis to ensure that none of the eigenfrequencies are hit, at a typical operating condition of this device. And then lastly, the thermal management analysis, where we're going to do a full-fledged conjugate heat transfer, convective cooling through the flow channel, and then conduction within the solid. So this is just that you're having a bit of a preview of what I'm doing. Good. Let's get started. We're gonna start with the simple pressure drop analysis. That's the easiest to do. And for that, you can see that I have no flow volume. So this is the inlet, right? This is the outlet. I have my the electronics down here, and here is the flow channel in here. And in order to run a pressure drop analysis, we want to isolate that flow channel. So for that, we're going to jump into SimScale's CAD environment. And that is not, a quick word on that, one of the, product philosophies at SimScale we have is that people come with the CAD model, they leave with their design decision. And that means that we want to make sure that all tools required for an end-to-end simulation experience are available on SimScale. And so as you can see right now, I'm basically, if you're familiar with other preprocessing softwares, this is a typical way of defining a flow volume. I just defined a seed face, defining two boundary faces. And what this does now is it isolates the flow volume as a separate part. What's happening in the background, SimScale uses Parasolid under the hood. So there's a live Parasolid session that is now calculating the wetted surfaces and creating a part from it. It appeared now. And what we want to do next is we want to get rid of all the other parts. So we're going to delete the other parts, and that will leave us with the isolated flow volume, this one. Beauty. We're going to export this right away into the SimScale project and can take it there through the actual simulation.
David, the fact that the simulation is cloud native, does that mean that it works much better with other cloud native CAD programs like your partner Onshape, or does it also work with any kind of CAD?
So let's start the other way around. So the Onshape is a fantastic example of how cloud tools can work nicely together. So there's a workflow from Onshape to SimScale where the CAD model never touches your local hard drive. So we natively integrate with them. You can bring in an Onshape model directly and simulate it on SimScale. And so obviously there's a lot of shared vision and there's a lot of shared approaches to the cloud, but that doesn't mean that it only works with cloud CAD tools. We bring in probably every proprietary CAD format can be natively imported, and if there's a CAD tool where we don't support a proprietary model or format, we have the natural STEP, XD, IGES, the standard exchange formats that you can bring in.
Very good. Great. Obviously, we're dealing with a SolidWorks model here, so you just imported it. So let's see what's happened now.
Yeah, good question. So this is our model. We just isolated the flow volume. And what I'm going to do, again, before I now set up the simulation, go back to the presentation and say, easy to learn. Wait, where is it? Easy to learn and use. Right? So let's keep this in mind as we're now setting up our first pressure drop analysis of this one. I just renamed this model to inverter CFD. I'm going to create a new simulation. Different, all SimScale is a general purpose simulation environment. I have access to a whole host of physics. We've seen that in the slide before. In this case, I'm choosing our subsonic analysis type for reasons that we're not going into here today. But I could have also chosen others. In this case, it's a good choice. We define a material. In this case, we're cooling. Let's assume we're cooling this piece of equipment with water. I want to assign a sort of the constraints to this model, or in this case, boundary conditions. We want to bring in 0.5 kilograms per second flow volume. Here's my inlet. And then lastly, I want to have a pressure outlet over here, meaning gauge pressure is 0. And that's literally it at this point. Now, before we go ahead, is just a quick recap. I brought in this model, I isolated the flow volume, I chose the material water, defined velocity inlet, pressure outlet. I now have all sorts of other settings that I could go into and define things, but I think the important aspect would have rotating zones if something would be rotating, etc. But in our case, we're really just interested in a quick first analysis. And the reason why I pointed out easy to learn, easy to use is that our approach to this is that as an end user, you should have access to all details. So you could now go into here and define the linear system solvers, like you could drive local mesh refinements, you could drive local mesh sizing, etc. So all things you might be used to from traditional simulation software, but you shouldn't be forced to. And thanks to the fact that this is in the cloud, there's a lot of heuristics. There's machine learning being used to select the instance, so the compute instance on which a certain simulation is being carried out, etc. And so there's a lot of automation built into it to make this easy to learn and easy to use. If this is not enough, right? If you happen to hit a wall on a certain model, the collaboration comes into play. So you have the ability to just bring up the chat down here. You have a little box down here, share project with SimScale support, and you can say you can start a chat directly with SimScale support team. And now, because this model is now shared, the simulation project is now shared, a simulation engineer of SimScale could now come into this project live, right, real time. I would see his or her face popping up here. I could see the interactions, and so we could in real time. Oh, Kim was answering. Just making sure I'm not annoying my colleagues with these demos. So we can in real time now make use of support over here. See, Guillermo could now help us already and jump in. The same is true for collaboration inside my organization. So I can go in here and say, I want to share this with someone else in my organization and give them access to it. And so the beauty again is because everything is on the server, everything happens in real time. You have the ability to, in a much more efficient way, collaborate and receive support instead of opening up Jira tickets and opening up support tickets and waiting for a couple of days. Everyone has access in real time to the same. To the same simulation project. Good. This was on collaboration. Now, while I talked all about this, let's remove the chat. Our simulation finished, and let's quickly carry this all the way. So I'm bringing up the simulation results now. Also, this can be done integrated in an integrated way in the same environment. Let's remove the cut plane and color this by pressure. This is likely the perspective everyone would be used to, right? So I'm having, let's change this to kilopascals. I'm having high pressure over here, low pressure over here. I defined this to be 0. We can also, inspect the point. So pressure over here I defined to 0 gauge pressure, right? And then I have, 130 kilopascals over here, and that's where I already can sort of gauge. I see the pressure drop across this channel. I can see that sort of my over here it might be not that nice. I'm starting to have already. I might need to rethink this corner here. Yada yada yada. Or also, I could now go through different design versions. I have these cut holes for cooling purposes in here. So I might want to, make them smaller, make them bigger, etc., depending on how important this aspect is to my design, to the overall product performance. And we could now, we're going to take a look at some other post-processings in a second. So we could now do streamlines, and we can quantify this, and etc. But that's not what this is about. Again, it shouldn't be a training session, an in-depth training session. I think the important part that I wanted to mention is that we went live from a CAD model over, preparing the geometry, defining the setup, defining the simulation setup, carrying out the simulation to a finished result in about 10 minutes, and had Kenneth and I not talk too much, we might actually, get it done in 4 to 5 minutes. And so I think the important piece here, going back to this again, is like we've done all of this in a browser window in a collaborative manner, fairly easy to use, fairly easy to learn. And that's something that we believe is key for, a differentiating factor of a cloud-native solution, and to really enable more engineers earlier in the design process to leverage simulation. So that's something I like to just stress at this point. Now, we said that's in the title of this webinar, we talked about this is multiphysics. Right? So far, this was not a lot of this was just physics. So let's continue at this point and see how the exact same workflow can be used, the exact same application can be used to define other simulations. For this, let's give this first a meaningful name. My pressure drop analysis. Next up, I want to simulate the vibration, the eigenfrequencies of this model as well. And in this case, we're going to go back to the full assembly, and we're going to use the exact same workflow. We're starting with this model, creating a simulation. In this case, we want a frequency analysis. On the left, you can see already the contacts are being automatically detected. In this case, we don't have any complex kinematics, right? There's nothing sliding, there's no hinge contacts, etc. So that's already good. Next up is materials. For the sake of, I'm just watching the time. We're supposed to wrap this up in 10 minutes. So watching the time, we'll simply assign everything aluminum. We do know that there's some, copper and tin down here, but for the purpose of learning, that should be good enough. We're assigning aluminum to everything. We do use the same way to define boundary conditions. In this case, we're having those 4 mounting points that we're going to fix. And we want to define, here you can define how many modes we want to compute for the sake of this webinar. It's just, okay, we're just going to say, 10 first modes. It's good enough. And I can run this. Now, to drive home those points, you can see that my mesh is being automatically generated. I could now go into a lot of detail in here. Drive local sizing. I could, go into more advanced parameters, specifically when there's, certain regions I'm interested in, or I'm doing a mesh sensitivity study, or these types of things. But if I don't do any of that, the application itself uses heuristics, machine learning models, in order to come up with good setups, good default setups for this. Also, another thing I haven't mentioned before is I can define the number of cores and the machine on which a simulation shall be carried out. But again, also here, if I leave this up to automatic, this is being automatically chosen based on, because it's a cloud-native application, there's a lot of data to learn from, and it's going to select the machine that'll give me the fastest results. So that's basically underway now. Now, this will probably take about, at guesstimate, maybe 4 to 5 minutes for the meshing, and then another 4 to 5 minutes for the simulation run. So we don't want to wait this long. We have about 6 to 7 minutes left, and so I want to make sure that we're on time at 45. So I don't want to spend too much time on the last simulation setup, but I at least want to touch it. And that would be the conjugate heat transfer analysis. In this case, we would need the flow volume and the CAD model together, because it's a conjugate heat transfer. I'm simulating water flow at the same time as I'm simulating conduction through the parts. We don't want to do this CAD preparation now, so we're just going to take a look at the simulation setup. So this would be a conjugate heat transfer analysis, and you can see here the setup again looks very, very similar. With the difference is that I have fluids and solids. I have both heat transfer and flow simulation boundary conditions. But again, the concept of this entire analysis is very similar again. Right? Now, lastly, to go full circle, I have something prepared. Let's go back to the SimScale dashboard. Just take a quick peek at how those simulation results look like once they are done. Again, I would guesstimate that the frequency analysis takes about 5 to 6 minutes, maybe 8 minutes. The conjugate heat transfer analysis would take probably an hour, maybe 1.5. Because it's a fairly, it's a 60-part model. It'll require quite some cells. So over here, again, our familiar model, and you can see on the left the 3 simulations, 2 of which we went through the full setup, 1 of which we didn't go through the full setup. Let's quickly take a look at the results. This is the vibration analysis. Oh, you can see I used a different material here, but you can see the boundary condition was exactly how we did it before. The mesh was generated automatically. And so we want to now take a look at the modes, at the eigenmodes and eigenfrequencies that were computed. So we're looking at the normalized displacement. In this case, we can see this is at 715 hertz. And as you're used to it from frequency analysis, you can now step through the different frequencies where eigenfrequencies appear. And you could now, of course, we could look at how important are those modes, and are the frequencies at which they are hit, are they in a dangerous operating environment, or are they could they lie in a field where those vibrations could be triggered by the operating conditions of this device? Of course, all of this is available as tables as well and plots, etc. So here I can see all eigenfrequencies and all modes, etc. Again, it's not supposed to be a training. I just wanted to make sure that you see this, full circle, the frequency analysis set up, and then all the way to the results. And then the last 2 minutes spent on the thermal management simulation setup. Again, I gave you a quick impression earlier. Right here we have the flow volume and all the parts of the actual assembly. Together, I've defined fluids, solids. I have defined a velocity inlet, a pressure outlet over there, and then an ambient convection boundary. So we have air taking away the heat from this enclosure, and then the water flow removing heat from within. And let's take a look at those results for the sake of completeness as well. And we could just see this simulation took about 70 minutes to compute. And again, without going too deep into result interpretation, we're looking at a result plot of the temperature. And so we can see the electronics components, as we would expect, are hot down here. Let's take a look at the water flow. And we have the streamlines of the through the water channel here. And I can see that the enclosure is getting hot there as well. And again, we could now go in, right? We would need to quantify, or we would like to assess the quantitative results on the critical electronic components. Are they operating in safe conditions? I could understand, sometimes there's a question of the enclosure shouldn't get too hot, right? Is that appropriately? Do I need to redesign, or do I need to make certain design changes to the water jacket? Yada, yada, yada. So these would now all be things that I could make informed design decisions moving further. Now, let's drive that home before we go into the Q&A. I'm not gonna, I don't want to go through the entire animations here again. So I think we talked about all of this. I think important for me was that this is, that there's more to it than just a browser, right? There's more to it than just cloud native. What this enables is simulation being done anywhere, anytime. It's easy to learn and easy to use for novice users to quickly pick up. A collaboration layer that enables both the SimScale support as well as simulation experts within the organization to support more, novice users in simulation. And then lastly, again, table stakes. We've seen a CHT analysis, an incompressible CFD analysis, and a frequency analysis on a, not the most complex model, but on a fairly on a not that easy model done in a very short amount of time. So capable and robust are key in today's worlds of ever increasing product complexity. And with that, I want to just mention before we go into Q&A that I would really encourage you, hopefully, if anything stuck from what I said, is that these simulations can be done. If you have half an hour or an hour at some point to play around with this and want to get your own impression of it, sign up for an account. There's step-by-step tutorials to very similar simulations as I've shown them. You can try them out yourself and see whether or not that's a tool that might be of use within your day-to-day engineering work. Kenneth, and with that, I'm done with the official part, and I think I said enough, so I'll make a pause now here, Kenneth, and let you take over the Q&A part.
Very good. Thank you very much, David. I'll let you browse through some of the questions that came in while, if I may, just make some observations about the demo that I've seen. I thought it was really impressive that things like meshing, for example, is completely automated. So, for example, if a novice design engineer who is relatively new to simulation handles something like this, he or she doesn't have to struggle with what kind of meshing is going to be appropriate because the machine learning and the software is intelligent enough to figure things out. So that's a very important thing. Maybe we can start with one of the questions that came in through the registration. In the meantime, David, if you could stop the screen share so we can come back on camera and we'll chat directly with our audience. one of the questions that came in during the registration process is about the hyperelastic materials. Could you perhaps talk at a wider range about the material database that come with SimScale and what kind of material it covers?
I stopped my screen share. I thought about jumping back into the application, actually showing it. So the material definition at SimScale is completely custom, meaning that you can. I saw a follow-up question on stress-strain curves somewhere. Maybe we can knock this off with this one already as well. Okay. That is, of course, you can define the material model in detail. You can upload stress-strain curves. There's multiple material models. Hyperelastic, elastoplastic, plasticity, etc. And you can upload all of them and define fairly sophisticated material models. Now, to the question of SimScale, SimScale does not come with a vast material library such as they are available out there, the MATLAB or other material libraries that aspire to be really complete, right, and then give you a lot of fine granular atomic choices around materials. That's not the case in SimScale. So what typically happens is that customer organizations upload their own and store and share their own material information within SimScale. That's the typical workflow or the typical way we're seeing people define material data on SimScale.
Very good. So let's start with this question about the interaction with CAD programs, right? Noah asks, design iterations require lots of CAD work. To avoid lots of cumbersome, time-consuming model transfer, SimScale would need competent CAD capabilities or associativity with the software that is used to create the model. Please comment. What are your thoughts on that? Obviously, people don't expect a simulation program to be a full-fledged parametric CAD program, but what's reasonable for people to expect?
Great question, and I couldn't agree more. I think I couldn't have said it better. what SimScale would need to have in order to make this practically useful, and I think both. Let's start with I've shown some CAD editing capabilities. At times, it's true that those CAD editing capabilities inside SimScale are enough to iterate through certain design iterations. But this is not what SimScale's CAD editing environment is meant for, right? So in case of doubt, there might be a missing function or missing functionality to do the design iterations that you need to. Also, one of our principles at SimScale is that we don't want to change the authoring workflow or the authoring system where a user or a customer is defining geometry in. And so that's why, yes, the upload is associative, meaning you can bring in a new CAD model, a new version of your CAD model, and of course, if you bring in a completely new model, right, that has nothing to do with the version before, SimScale's associative update will not pick this up, right? And so, but if the version is closed and specifically from the same CAD system, ideally if the CAD system preserves IDs over topological changes, then you can simply swap the geometry within SimScale, and all boundary condition assignments, mesh refinements, etc., are preserved. So to summarize this, SimScale is used in a lot of iterative design workflows, and so the quick iteration between a design change and the simulation is key. And so as such, this is an area where we've invested a lot, where we still continue to invest because there are certain CAD systems where it works better than others. But this is something that is already possible today. Yes.
All right. Somebody wants you to review the importing options for proprietary material information, including SS curves. I wonder if it's something you can talk through about how to do this.
Yeah, so you would bring in I don't want to start now a screen share again, but in the material dialog where you would add a material, you have the possibility to define the material model you want to use, and then upload, depending on if that material model supports a stress strain curve or needs a stress strain curve, you would upload it either as a CSV file. You also have the option to find, in this case, a CSV file that you would bring in. Yes.
All right. There's a question about maybe perhaps a formula that you can give on how much a particular simulation job might cost. Do you have any guidance?
I mean, the simulations I've shown. So SimScale is the pricing model of SimScale is an annual subscription, and so as a subscriber to SimScale, you then have a certain computing quota, and the simulations I've shown were like barely used any computing quota of as it relates to an annual subscription of SimScale, and so as such, the costs of the simulations we've seen would be marginal, right? Not something you would think about as you use SimScale.
All right. Well, there was somebody who I guess may have missed how the flow boundaries were defined when you were demonstrating it. I thought it was pretty easy to define. Could you perhaps point out some of the things that you did?
Oh, yeah. I mean, I'll not. Kenneth, do you want me to start screen sharing it? I think we're anyways running short on time, so I'll.
You could do it if you want to. You could do it because we still have probably about 6-7 minutes before we wrap up. Go ahead. So.
All righty. Let's quickly jump back into SimScale.
Yeah, very good. So there is a lot of good questions about technical questions. So I think it's a sign that all of our audience are actually thinking about doing something. So we hope you will take advantage of this because there is a link that we can share afterwards so that you know where to go and get access to a demo and also the tutorials that are available from SimScale. So here it is. The screen is live again.
Yes. So let's go back to the flow boundary condition. And so this was the pressure drop analysis I've shown earlier, right? And let's delete one of those boundary conditions, or let's delete both. And so on the left, you can see this is the pressure drop analysis, right? And one of the child items of that tree of this analysis is boundary conditions. And so just with the contextual add, I can add a velocity inlet. And you can see that then is, this is, I think, the typical, like most CAD systems work. This is now marked active. And so I just click on the face and I can see this boundary condition is now assigned to this face. And I can then further specify how this boundary condition shall be defined. You can see, there's flow rates, fixed value. I could also do volumetric flow, etc. This defines my inlet over here. I must admit the assignment color is very close to the model color, right? So that's not 100% obvious here. And then same is true for the pressure outlet. So I would choose a pressure outlet, define this over here, right? And the gauge pressure 0, it's good enough. And again, like I could just run this. Let's do it for the kicks, just running it again. So these were the two boundary conditions that I assigned. That's how it worked.
Okay, very good. Thank you very much. Audience, if you have any more questions, feel free to type them in. We can probably address one or two more. I think that's how much time we still have. In the meantime, David, there is one question that we have already partially addressed, which is about the high-powered GPU. I guess it's because it may be a thing that people are interested in if they have invested in a pretty professional workstation GPU in their own workstation. SimScale being a SaaS model, does it interact with the local GPU at all, or how does it work?
So a strong local GPU helps, but is not required. And the reason why I say it helps is that there's certain aspects in a simulation workflow, such as, we just seen the assignments of boundary conditions and like rotating a CAD model, etc. So there's certain aspects where we do leverage the local GPU. So in this case, it's not pixels that are being streamed, but triangles are being cached in the browser, and we can then we can leverage the local GPU, and that is good because you then have it's 100% responsive. So there's almost no difference anymore to a local desktop software, and so to a certain extent, a good local GPU helps, but there's no such thing as like the local GPU being used for any solve operations or any heavy lifting during the solve. So that's where a local GPU can help.
Understood. All right, very quickly knock this one off then. Does this work with Autodesk Inventor models?
Yes, we have a lot of customers using Autodesk Inventor. You can bring in the native IPT file and it'll work.
Okay, so let's make this one the last one, David. Are there any manual meshing capabilities which is useful for making simple study models?
Yes, so manual meshing can be done. You have, again, it a lot depends on it. There's even multiple meshing algorithms in SimScale. There's Octree, there's Cutzell, there's Cartesian, there's standard Delaunay tetrahedral, etc. So there's many different algorithms, and each of them come with different ways of how you can manually drive a mesh. But again, going back to what I said earlier, SimScale is about making simulation technically and economically more accessible. So we don't require any of these steps compulsory, right? That where a user has to go through them, which is often the case in other softwares. Here, automation heuristics are being used to drive a very good mesh. But if a user, is advanced enough or has a certain reason to drive a mesh manually, of course, this is possible.
All right, David, thank you so much. I think there may be some more questions, but perhaps you'll work with your tech staff to respond to them in writing. In the meantime, this is the link to, by the way, the audience, if you'd like to go and try out the demo that you've seen so that you can experience for yourself what it is like, and also take a look at additional information about SimScale. So I'd like to thank David for sharing his time and giving us a live demonstration of how SimScale works in the cloud. And I'd also like to thank SimScale for sponsoring and making this episode possible. Until next time, ladies and gentlemen, I'm Kenneth Wong, Senior Editor for DE 24/7, and we are signing out.